Hey everyone, welcome back to the channel. In this video, I'll show you how to fine-tune a llama model on your own dataset. We will start with the basics, what fine-tuning actually means, what LoRa QLoRA are, then explore our dataset, and finally walk through the training course step by step. So let's get started. So first, what exactly is fine-tuning? Imagine a large language model like Llama as a student who has already read the entire internet. It knows a lot, but maybe you want it to focus on your domain like medical Q&A, customer support, or in our case, travel related conversations. Fine tuning means we take this already trained model and continue training it on our smaller custom dataset. This way, the model does not relearn from scratch, it just adjusts the knowledge to better fit your task. This makes the process much faster and cheaper compared to the full model training. Now in the second section, let's understand about the LoRa and QLoRA techniques. So the big challenge is Llama has billions of parameters. Training all of them would take huge GPUs and massive costs. That's where LoRa comes in. LoRa or low rank adaptation freezes most of the model's parameters and only trains a small set of additional weights. Think of it like attaching a small add-on to a bike. You don't rebuild the whole bike, you just add a small lightweight part that changes how it rides. Then comes QLoRA. QLoRA is quantized LoRa. This reduces the precision of the model weights to 4-bit or 8-bit. So it uses much lesser memory while still keeping accuracy. This makes it possible to fine-tune even larger model on single consumer GPU. Now let me explain the LoRa QLoRA through a visualization for a better understanding. Now look at this visualization. Here in the visualization, first focus on the full fine-tuning part. So look at this red matrix. It represents all the weights in a neural network layer. In full fine-tuning, every cell here gets updated during training. That's why it needs massive memory because you are storing weights, gradients, and optimizer states for a billions of parameters. Now look towards the LoRa. LoRa changes the game. Instead of updating the entire weight matrix W, we freezes it. See the gray color. It stays locked. Then we add two tiny matrices B and A, the green ones. These are way smaller than the original. The formula for this is simple. Here the update is like W dash equals to W plus B cross A. Your new weights equals to frozen weights plus this small update. Since B and A are only 0.1% of the original size, memory drops from 80 GB to around 24 GB. Now we are talking about affordable GPUs. Now let's focus on the QLoRA size. QLoRA is quantized LoRa. QLoRA goes even further. See how the frozen matrix is now yellow. That's 4 bits quantization. We compressed from frozen weights from 16-bit to 4-bit precision. That's a 4-cross memory reduction. The trainable matrices B and A stays in full precision because they are actively learning. But the frozen based model, it can handle lower precision just fine. Result, you can fine tune bigger models on just 12 GB of the memory. Now see the comparison table. In the full fine-tuning, the 100% trainable parameters are required, and here 0.1 to 1% of the parameters are required, and same here. In the memory part, here very high memory is required because we are doing the full parameter fine-tuning. Here medium memory is required, but in the QLoRA side, we are further compressing the model into 4 bits. That's why 12 GB of memory is required. In the training speed, here the training speed will be very slow. Here it is much faster, and same here. Now let's talk about the model quality. Here the model quality still remains excellent because we are training the model from the scratch. Here are the comparable. In the hardware needed part, Here the bigger GPUs are required for full fine tuning. Here single GPU is required in the LoRa, and here consumer GPU is required. Now let's understand about the dataset format. We are using a JSON file, which is basically JSON records separated by new lines. Each record has a prompt and a completion. The prompt is the user's question and the completion is the assistant's answer. For example, here inside the prompt, the question is like, how do you select MX versus IHG? In the completion, the assistant will answer comfort, cultural depth, seamless service. We then formatted the dataset into conversational style using special tokens like IAMStat_user and IAMStat_assistant. This way the model knows who is speaking. Finally, we split the dataset into training set and the evaluation set. Training data is what the model learns from, and the evaluation data helps us measure how well it's learning. Now I will walk you how to fine-tune the LLaMA 3.1 model using Hugging Face, PEFT and LoRa. Let's dive right into the code. Here I use the Kaggle Notebook for fine-tuning the model, and here I use the two T4 GPUs for efficient fine-tuning. Now I'll explain each step of the notebook. First, I just import the warnings library and tell Python to ignore warnings. This keeps the notebook output clean so I can focus on the important results. Next, I install the key libraries that make everything possible. So the first library is Accelerate. This library helps us to run models efficiently across CPUs and GPUs, and TRL is used for supervised fine-tuning with SFT trainer, and PEFT is for parameter efficient fine-tuning methods like LoRA. Transformers is for Hugging Face main library for models and tokenizers. Bits and bytes for loading the model in 4-bit quantization, saving a huge amount of GPU memory. And pandas is for handling our dataset. So together these packages gives us the ability to load a massive model, shrink it down and fine tuning it without needing super expensive hardware. So after installing the libraries, I am importing all the Python libraries like PyTorch, Hugging Face classes, and PEFT modules. This basically sets up the building block of our pipeline, data, model, tokenizer, and training. Now I am choosing the base model. So in this step, I define my base model as Meta LLaMA 3.1 Think of this as the foundation. The model has already been trained on a huge amount of text. Now we will teach it to specialize in our dataset. After this, I am logging into Hugging Face. Since we are downloading weights from Hugging Face Hub, I log in using my token. This also allows us to upload the fine-tuned model later, so we can reuse or share it. After this step, I am loading the model and tokenizer with 4-bit quantization. So here I define a helper function get model and tokenizer. This loads the tokenizer which breaks text into tokens and the model, but in 4-bit mode. Like here we use 4-bit because 8 billion parameter model is massive, but quantization reduces memory uses drastically. This means you can fine-tune it even on smaller GPUs like single A100 or even consumer GPUs. After this, the model will be loaded into the GPU memory in the compressed format. So you can also see the model is taking around uh, 7 to 8 GB of the memory. As the base model is loaded into the GPU memory, now I'll test my base model on some user input. So my user input will be like Python code for reversing a list. So this helps me to see how the raw model is performing before I start training it on my own dataset. So Also here I specified two helper method. The first one is the formatted prompt. So this function takes a user input or question and wraps it into a template with special token like I am start user and I am start assistant. For example, as in my case, the question is Python code for reversing a list. The function transforms it into something like I am start user, Python code for reversing a list, I am and I am start assistant. So this tells the model, okay, here's the user speaking. Now it's your turn, assistant to respond. By using this consistent prompt, the model clearly understands when this user's part end and when the assistant should start generating. Later, when I fine tune on my dataset, I use same style so the model learns how to respond in a conversational manner instead of just predicting text randomly. So let's try this example with this formatted prompt. First, I need to execute this cell. Now, here the assistant is responding in this way. Next, I load my dataset which is in JSON format. So here's my dataset. It contains two fields, prompt and completion. Prompt is the user's questions and completion contains the assistant's response. So this is travel related conversations. I then reformat each row into chat style template with users and assistants tag. So here you can see in the data frame the prompt completion part. So I am applying a lambda function here. So before each user's question, I am appending the special token I am start, and after ending the user's question, I am appending I am end. So before starting of each assistant response, I am appending this tag, and after completion of assistant response, I am appending this tag like I am end. So this format is exactly what model expects during training. So let me execute this cell. So after this operation, the data set will be in this format. So the text will contains the prompt and completion in the chat style format. Now after reformatting, I am removing this first two columns. I am only keeping this text field inside the data frame. So now our data set is ready. So here I am specifying the output directory where I will store my fine-tuned LoRa adapters. Later I can load these adapters back into the base model and get my custom fine-tuned version. Now here I define my LoRa configuration using LoRa config. This basically tells the PEF library how I want to apply LoRa fine-tuning to the LLaMA model. Let me break it down. So R equals to 16. This is the rank of the LoRa matrices. Think of it as how much we compress the trainable weights. A high value means more trainable parameters, but also more memory uses. 16 is a good balance for our dataset. LoRa alpha is a scaling factor that controls how strongly the LoRa updates influence the model. And target modules is basically list of all modules inside the transformers where I actually want to apply LoRa. And these are basically the attention and feed forward layers where most of the heavy computations happens. By targeting them, I can get the maximum efficiency. And next one is the LoRa dropout. This applies dropout to the LoRa layers during training, which helps preventing the overfitting. Bias equals to none means I am not adding any extra bias parameter to the LoRa layers. I am only updating the low rank adapters. Task type equals to casual LM. Finally, I specify the task type as casual language modeling because I am training a left to right generative model like LLaMA. So overall, this configuration tells PEF
don't fine-tune the whole model. Instead, just add small trainable adapters layers inside these specific modules. This is what makes LoRa so efficient. Instead of updating billions of parameters, I only train a tiny fractions while still getting great results.
Here I is setting up my training arguments using Hugging Face training arguments, and I define my output directory where my fine-tuned model will be saved, and the batch size per device is 4, but since I also use gradient accommodation steps equals to 16, it effectively stimulates a larger batch size without using too much GPU memory. I use the Pace Adam W optimizer in 32-bit for efficient training. The learning rate is 2 e raised to power 4 with a cosine scheduler. This slowly decays the learning rate over time. I log progress every 10 steps, save checkpoints every 500 steps, and train up to 3 epochs or maximum 250 steps. I also enable FP16 mixed precision training to speed things up and save memory. Finally, I explicitly set the tokenizer's maximum sequence length to 1024 tokens, so the model knows how long each input can be during training. Now I am splitting my dataset into training and evaluation. I am using 90% of my data for training and 10% for the evaluation. And after this, I set up the data collector using the data collector for language modeling. This basically prepares the data before it goes into the model. I set MLM equals to false because I am not doing mass language modeling like BERT. Instead, I am training a casual model that predicts the next token. Next, I create my SFT trainer. Here I pass in the model I am fine tuning, the train and evaluation dataset, the LoRa configuration I defined earlier, my training arguments, and the data collector which handles batching and tokenization automatically. So, in short, that this trainer is the engine that runs the actual fine tuning process with all the configurations I set before. Here I actually start the training. I use perf counter to capture the time before and after training so I can calculate how long the process takes. Then I call the trainer.train which kicks off the fine tuning with all the arguments, datasets and configurations I set earlier. Finally, I print the total training time in seconds just to quickly check how long my fine tuning run took. So as I earlier run the fine tuning job, so it took around 136 minutes on 2 cross GPUs, uh, and my dataset has approximately 5,000 rows. After running the trainings, here's my result. You can see both the training loss and the validation loss was decreasing. So for example, the training loss was around 2.09, but by the step 250 it dropped to around 0.17. The validation loss also followed the same trend, which means the model was not just remembering but actually learning to generalize. I also tracked metrics like entropy and mean token accuracy, and the accuracy started around 78% and the improved to over 92% by the end of the training. That's good sign. It shows the model got better at predicting the next token as training progressed. And finally, the whole training run took around 8,200 seconds, which is little over 2 hours and 15 minutes. So that wraps up the training part of this notebook. In the next video, I'll showcase how to run inference with the fine-tuned model and how to merge the base model with the LoRa adapters. Till then, if you like this video, make sure to hit the subscribe button and stay tuned for more. I will also be sharing this Kaggle notebook with all of you so you can try it out yourself. Thanks for watching and I'll see you in part 2. Bye.